Swayam Prabha. Digital India. Educated India.
So, in the previous lecture we discussed TXY diagram, vapor liquid equilibrium, and we talked about if we fix the pressure and temperature, then the mole fraction of components are fixed in both the phases liquid and vapor. We talked about tie lines, we discussed the dew point curve, bubble point curve, starting with a superheated vapor of binary component system. If we cool it, start cooling it, then we get this dew point. If further cool it, we have this bubble point curve. All right. So today what we do for distillations, we also have different approach to address a variety of problems. For example, instead of working on TXY, we can also have HXY diagram, enthalpy XY diagram. So this, so that essentially there are two approaches to design this distillation column. One is based on TXY, and one is based on HXY. So we take up this new new type of curve HXY, and we will see how we can construct this curve. Okay. So now we have this enthalpy concentration diagram. All right. So here, just like in the previous lecture, we had this TXY diagram. All right. So we had X, Y, T here of component B and boiling temperature of component A, and we said that if we fix the pressure here and we choose a temperature, then the mole fraction Y in the vapor phase and the mole fraction X in the liquid phase are fixed. So similar to this TXY diagram, we can also have HXY diagram. Okay, because once the temperature is fixed and mole fractions are fixed, one can calculate the enthalpy. Okay, so before we calculate HXY, let's see how we define HL, enthalpy of a saturated liquid, and HV, enthalpy of a saturated vapor. Okay, so HL is defined as CL TL minus T0 into molecular weight, average molecular weight, plus we can have del HS, which is heat of solutions. Generally for ideal solutions, heat of solution is taken to be 0. So for ideal solutions, we don't have this term here. So what it is essentially, we have binary components at the temperature of TL. T0 is a reference temperature. So if HL is saturated, or enthalpy HL represents the enthalpy of a saturated liquid, then TL is Tsat. So essentially we heat, this is a sensible heat components, and we heat this fluid, say from some temperature T0 all the way till TL. Okay, so HL equals CL TL minus T0 M average, where M average will be X into MA plus 1 minus X into MB. So essentially we have some kind of weighted average here. So HL, enthalpy of the saturated liquid, is nothing but specific heat of the liquid CL multiplied by TL minus T0 into molecular weight average. We are neglecting this heat of ideal solutions. Similarly, we have HF, HV, saturated vapor enthalpy. All right, and the way it is defined here is Y, or calculated CLA molecular weight A TD minus T0 plus lambda A MA. Okay, so let's look at what we have written here. We are essentially taking this pure component A and we heat to the temperature Td. So where Td is the temperature, let's say saturation temperature here. All it means, we have taken this component of A, pure component, we have heated till Td, liquid gets vaporized, so lambda A into Ma, and then it is getting mixed with component B. So 1 minus Y CLB, we have molecular weight Mb plus, multiplied by the temperature. So we have Td minus T0 plus lambda B into Mb. Alright. So these two components here and here, these are unmixed liquids. Okay. So essentially what all it means, that two components A and B, they are heated from temperature T0 to Td. Then the component B gets vaporized. So we have this component lambda B Mb, where lambda is a latent heat of vaporization for component B, and lambda is the latent heat of vaporization for component A. So the two components are heated, vaporized, and then they are mixed to obtain this saturated vapor enthalpy. Okay. So essentially with this we can obtain HXY diagram. So we have X, Y, and we had, so if we fix the mole fractions of component A in the vapor and the liquid phase, we can obtain curve like HL, saturated enthalpy, enthalpy of the saturated liquid, and we can have HV, not necessarily linear or parallel, HV, enthalpy of the saturated vapors. Okay. So if we fix the mole fraction X, then we have HL, okay, and corresponding to this mole fractions we can have this HV. So this is HL versus X, this curve, and we have HV versus Y. Okay. So now if we recall the previous graph for TXY diagram, if we plot TXY diagram, okay, so we have T temperature here and X and Y, and if we choose a tie line, that means this Y mole fractions, this is in equilibrium with X. So if we have Y and X fixed here for a given pressure and temperature, we can also generate, if you recall, Y versus X diagram. So essentially we can also have equilibrium curve like Y versus X. So we have Y here and YX here, and we know we can take a component projections from here X here, we can bring Y to this 45-degree lines, we can take, then we can extend here. Okay. So if we take it here, we can extend here to obtain this coordinate. Similarly we can obtain some other components, other coordinates here. Okay. So we have Y versus X, and we have TXY diagram. Now here also if we take this projections of X and Y and we construct this HXY diagram, which we have done right here, HXY, so this would be HV curve, this would be HL. So if we take this projections here HL, this Y right here, and we take this projections for coordinate X here, you can see that whatever if we connect these two, this will become our tie line. Okay. So now let's go back to this figure and the figure here. For this Y and X at this temperature, this is the tie line. And if we fix X and temperature, enthalpy of this component is fixed here for this liquid. Okay, liquid phase, saturated liquid phase. Similarly, fixing Y and fixing this temperature, we have fixed the enthalpy here. And the two we are trying to mark on this curve HY. How do we do this? X, we have taken the projection here from the top, and Y we have taken the projection here, that is saturated HV curve and HL curve, and we connect to make this as tie line. Okay, we will like to redraw this one top of the other. So let's start with TXY diagram again. TXY diagram. So we have this tie line, and we take the projections on this HXY diagram. So we have H, we have XY, we have this HV, which we have calculated or we have obtained from that expressions which we had earlier, HVHL. All it means, now if we take this Y here and we take this X coordinate here, we can draw this two line. This would be the tie line representing the equilibrium component. So this tie line essentially is same as the tie line we have here. Okay, that's one thing. Now, right, so and similarly, if we choose, let's reconstruct HXY diagram again here. Okay, so if we have H, V, and we have this HL, let's take two coordinates here. One is M and one is N. Now if we fix M, so that means coordinate is marked here, say ZM, HM, and we choose N, whose coordinate is marked as HN, and we have this ZN. Okay. Now if we mix these two fluids, so that means fluid with the enthalpy of HM, it's a binary components consisting of A and B, and another fluid of enthalpy HN with the mole fraction Zn. If we mix these two streams or these two fluids adiabatically, then one can show that the resulting component, resulting fluid's enthalpy will be on this straight line. So this is what we are trying to prove here, that if we mix M, whose coordinate is HM, and ZM, N, whose coordinate is HN, and Zn. So here we have chosen Mn, which is superheated vapors. So this is saturated vapor, saturated liquid, and this region is for the vapor phase. So this calculation should hold good for any 2 points on this HXY diagram. So for example, so if we choose M here and N here, and we mix these two fluids adiabatically, then we can write material balance, we can write energy balance like this. So we have now P equals M plus N. Okay, so we are talking of some moles of N is mixed with moles of N to give moles of P. Now if we make a species balance, P into Zp equals M Zm plus N Zn. Alright, so Zn would be the mole fraction of A in this binary mixture of A, N, and Zm is the mole fraction of A in the binary component of binary fluid of M. And when we mix these two, we have this fluid P, which is nothing but M plus N, and this has a mole fraction of A as Zp. Okay, so this is a species balance. This would be a total balance. We can also make enthalpy balance. P, Hp here, M, Hm plus N, Hn. Okay, so with these three equations, one for the total balance, one for species balance, and one for energy balance, one can show that can get a ratio of M by N, Zn minus Zp over Zp minus Zm equal to Hn minus Hp over Hp minus Hn. Now let's go back to this curve again. So we have H, X, Y diagram. Alright, so instead of Txy, we have this H, XY diagram, saturated vapor curve and saturated liquid curve. In this space anywhere we have two components M and N. We are mixing these two fluids adiabatically, that means there is no heat loss here, Q 0. If we mix these two, mark with the coordinates from these equations, it is easy to see that the coordinate of P will be on this straight line joining between M and N. See, this is what we have. This is Zm, this is Zn, this is Zp. So Zn minus Zp and Zp minus Zm, this ratio will be same as M by N, and M plus N, we have seen this equal to P here. Alright. So this is nothing but equation of a straight line passing through HP, Zp, Hm, Zm and Hn and Zn. So whatever we have the relation for M by N from first two, we can also obtain the relation in terms of Hn minus Hp. So this would be Hn here, this would be Hp here, and this would be Hp. So one can show by the coordinate geometry that this P lies on a straight line between M and N. Okay, and M by N, which means if you look at here again, Hn minus Hp over Hp minus Hm is nothing but the length of Pn. Okay, so Hn minus Hp, this will be the same ratios as the length of this Pn over this Pm into length. Alright, so what we have done now so far, that we started with HXY diagram. We said that just like we have TXY diagram, we fix the temperature, we know the mole fraction X and Y, pressure is fixed, enthalpy of this binary components of A and B corresponding to X and corresponding to Y will be fixed. One can calculate knowing the sensible heat and the latent heat of evaporations. We calculate the sensible heat of the liquid, know the specific heat capacity CL, the temperature is raised, cold feed from T0 to all the way till the saturated curve. So CL into TL minus T0 multiplied by the molecular weight. So you have raised the fluid temperature to the saturated level. Now to calculate the enthalpy, what we did, we said that we have A and B, both of them are raised to this saturated vapor curve, that temperatures. Okay, so the mole fractions of A and mole fraction of B in that proportion, it's raised to that temperature. Mix them adiabatically. Okay, first you have to heat it to the saturated temperatures, vaporize them and then mix them together. Okay, in that case we get your HV curve. Once we have HL and HV curve, HXY diagram is ready. Now we are saying that in that plot anywhere, if we choose 2 points, which is M and N here, that means now we are mixing the two fluids A plus B with the coordinates or properties mole fractions Zm, enthalpy Hm. We have another A plus B which has mole fraction Zn of A, mole volatile components, and enthalpy Hn. If we mix the two together without any loss of energy adiabatically, then we have now the mixtures which will be now P M plus N. So 50 moles of 40 60s. Now we have 100 moles, and the enthalpy of this fluid, the new fluid which we have now, if we plot on the same HXY diagram, should lie on the straight line between M and N. This is what mixing rule we have. Okay, we are going to make use of this property to do some more calculations on HXY diagram. So let's try to understand this mixing rule again, because this is what we are going to do it time and again. We have a distillation column, several trays, one vapor leaves one tray, goes to the next tray, liquid trickles down from one tray to another tray. So one can make this energy balance to show that we have two fluids which are getting mixed together, right, to have two new different streams which are leaving the trays. So there also one can do this mixing rule, what we have done now. So it's very important that we understand the coordinates of different components, different streams on this HXY diagram, the way we have done on TXY diagram. Okay, so let's do this mixing rule again. We have this Hx y diagram. Okay, so this is x, this is y. We have this enthalpy HL, we have this saturated vapor HV. Okay, now here, as we said that on this anywhere this HXY diagram, we can take two streams. We chose P and N. In the earlier example, both were superheated vapors, so we mix the two. Our third component, the new mixture, will have the enthalpy which will lie on this straight line. This is how we got the equation of the line. This is true with anywhere on these 2 points, which means now if we choose, say, C, all right, and draw any straight line here, say it cuts this curve on E and this curve on D. One can say that what is the C? It's the result of adiabatically we are removing saturated liquid D. All right. So if we take this saturated vapor E from this, if we remove this saturated liquid D, we should be able to show that the resulting mixture will be C. All right. Or if we choose the C, superheated vapor, mix with this saturated liquid D, one can show that we are going to get E. So whatever we have apply this mixing rule, A, M and N gives rise to P. One can also say that from P, if we remove M, we can get N. The same things, right? Writing like M plus N equals P, or N equals P minus M. So similarly here, one can say that this E, saturated vapor, what we have here E, is nothing but mixing this saturated liquid D and superheated vapor this C. Or C is produced if we remove this D component, D, this coordinate here, or the fluid of this specification D from E by adiabatically, we will get E here. So let's write down here that C is a result of adiabatically removing saturated liquid D from saturated vapor E, and also make a note that this DE is not a tie line. All right. So this also very important that this D is not necessarily the tie line. We will talk about this later. Maybe the tie line is DE prime here. The tie line only if this component here, this mole fraction, is in equilibrium with this mole fractions, and that has to come from TXY diagram. All right. So if this is a TXY diagram, then this is a tie line. We have this Y component. This is X here, mole fractions. If we now take the projection on HXY diagram, which we have done earlier. So if this is your HP, this is your HL. If we take this here, it will intersect here, and if we take the projection here, this intersects here. If we draw this line here, then this will be a tie line, because this Y and X, they are saturated compositions of saturated vapor and saturated liquid at the same temperature. Okay. So in this case, not necessarily this DE will be a tie line, because they may be at different temperatures. If I take this point here and take some other temperature here, okay, and then take the projections on this, all right, and this, and then we draw this line. Now this line is not a tie line, because they are the two components, not a tie line, because these two components here, mole fractions corresponding to this and mole fractions corresponding to this, they are not the same temperature. Okay. So it's very important that what we are trying to say here, we understand that we are applying a mixing rule. It's only a mass balance, total mass balance, or it's total species balance. We are saying that if we add C and D, we will get E. If we subtract D from E, we will get C. If we subtract C from E, we will get these components, and not necessarily this D or E. They are the equilibriums. So not necessarily this would be the tie line. It's possible that it could be on tie lines if they have the same temperature as given from here. Okay, and once again we can do the calculation which we did earlier, that this E can be seen as D plus C. Okay, or we can also write as C as E minus T. So that's what we said. C is a result of adiabatically removing saturated liquid D, so saturated liquid D from saturated vapor E, but not necessarily at the same temperature. If they are the same temperature, of course it will be a tie line. Right now we are just applying a mixing rule. E equals D plus C. We can also write E into HF, HE equals D HD plus C HC. Alright, so these are the respective enthalpies of E and D here. All we have done, we have just applied energy. We can say it's adiabatically mixing, so this is 0 here. We can also make a balance for species balance YEE, so this would be DXD plus CZC. We can always arrange this DXD plus C as E minus D into ZC, and then one can show that we get E by D YE equals XT plus E over D minus 1 ZC, or E over D can be written as XD minus ZC over YE minus ZC. This will also be equal to HC minus HD over HC minus HE. So look at this, E by D equals HC minus HT over HC minus HE. This is what we are trying to say here, that on HXY diagram we have HV and we have HL. We have constructed this from TXY diagram, knowing the sensible heat, latent heat of evaporations for component A and latent heat of evaporation for component B. We have constructed these two curves here. Okay, and we choose two components, two fluids E and D, and if we subtract D from E, we will get C here, or if we subtract or if we add C to D, we are going to get E here, and we are saying that these are not, ED need not be a tie line. Okay, so this is your ZC, this is your XT, we have YE, and we have 3 enthalpies corresponding to these mole fractions. Okay, so far what calculation we have done, we have created HXY diagram. That's it, that's one. Once we have HXY diagram, then we apply this mixing rule. Anywhere on this HXY diagram, if we choose two components, two fluids, A plus B and A plus B, either they are saturated vapor, saturated liquid, one of them is vapor, one of them is saturated liquid, doesn't make a difference, right? We are all going to apply mixing rule. Take these two components and mix them. The resulting mixture coordinates, enthalpy of the resulting mixtures has to lie on the straight line joining the two components. This we get from the mixing rule. Okay, this we did for HXY and we did it also for YXY diagram, on TXY diagram. There also, if we take the two components, apply this mixing rule for the total moles and for the species balance, one can show that we will get the similar scenario, that we have a straight line and the two components which are going to be mixed, they lie on the same straight line as that of a resulting mixture. Okay, because we are going to make use of this in our next calculations. So now based on this, now we start the first unit operations. Of course we are in the distillations, but we have also single stage vaporizers. We call it flash drum, and it's a one stage flash drum which is going to be the the block. We will start from this single stage as a building block for the distillations. Okay, so essentially what we have in a single stage flash drum, that you take a liquid, so feed a certain composition, say ZF, and if it's a cold feed, one has to heat it, So you have to supply heat Q, bring it to this some saturated liquid, and there it should be pressurized so that you can flash it to the lower pressure, and then you can have larger separations. If you recall, in our previous lectures we talked about effect of the pressures. So if you have TXY diagram at certain pressures, and if we increase the pressure, then we said that most of the ideal fluids or the binary components fluids, their separation will be smaller. In other words, this envelope of TXY diagram will become smaller. So for the same temperature, now we have small separations. If we decrease the pressures, then if there are no isotrops or the components are behaving as ideal fluids, then we have this larger separations. So when we want to have this distillations, separation in single stage operation, vaporizer or flash drum, generally what is the practice? That you take a fluid, heat it, bring it to a saturated temperatures, and it should be pressurized at high pressures, so that now you can throttle it and flash it to the vapor and the liquid. Okay, then you will see a separation XY. So it's a single stage. If we understand this, draw it on our TXY diagram, on HXY diagram, then you will see that when we take up the larger distillation column where there are different stages, trays, this will act as a building block. Okay, so let's start this single stage operation or single stage vaporizer, which is nothing but flash vaporizations. So we have this single stage operation, which is nothing but flash vaporization. Okay, so essentially what we have here, liquid mixture is partially vaporized, the vapor is allowed to come to equilibrium with the residual liquid. With the residual liquid, and the resulting vapor, liquid phases are separated and removed. Okay, so let us draw this schematic of this single stage operation or flash vaporizations. So essentially we have a flash drum here. It's a very simple device, a flash drum in which a feed is or liquid is brought in. So let's say the feed flow rate is F moles per unit time, so moles per second. Composition of this fluid, this feed is ZF. So we have binary components AN plus A plus B, and when we say ZF, ZF is the mole fractions of more volatile components A. That's the convention. So 1 minus ZF is a mole fraction of less volatile components here. So ZF and this fluid, once we have F fixed ZF, then enthalpy of this fluid is HF, calorie per mole. Now this fluid in general is cold, so it's brought to a heater. So where we are giving this heat Q at say a certain rate, calorie per second. So the heat is given to this fluid Q, and we said earlier this fluid is actually pressurized. So the pressure upstream is P1, or this boiler pressure is P1, its throttle to P2, okay, before it's flashed into this. Now let's examine this state of this fluid which enters the column or after throttle. Alright, so here this mole fraction of the feed is ZF, which means the mole fraction will remain the same here as ZF. Okay, total mole fractions, it will not change here. Enthalpy will be, however, HF, plus Q over F, because we have increased the enthalpy, we have added heat here, we are adding heat at the rate of Q calorie per second, and molar flow rate is F moles per second. So now the enthalpy of the fluid which enters the tram is HF plus QF. Okay, feed rate is the same as F moles per second. We talked about this, that this fluid has to be pressurized, right, to a relatively higher pressure, so that we can throttle it, bring down to the lower pressure P2, and then we can achieve larger separations. So now after this, so when we flash, then there is a vapor and this liquid, the two liquids, two phases, they are brought in intimate, in contact with this, and then the vapor is separated from here and the liquid is separated or drained from here. So it's a very simple device, right, and we will see that the analysis here, that's more important. Whatever we do the analysis on TXY diagram or HXY diagram, that becomes our very basic, very fundamentals to do the calculation for distillation trace wise. So we have the liquid, let's say it's withdrawn at a rate of W moles per second, vapor drawn as at a flow rate of say D moles per second or moles per time. Enthalpy of this liquid is HF, saturated liquid, and here enthalpy of this vapor, saturated vapor, is HT calorie per mole. Mole fractions, let's use XW, and let's use the mole fractions YD, the vapor phase here. Now we said that HD and HW, these are the enthalpies of saturated vapor and liquid respectively. That means once we have this vaporizations or flashing, two phases, they have been brought in intimate contact, sufficient time has been given so that the leaving streams are in equilibrium. In that case only HD and HW, these are the saturated enthalpies of the saturated phases here. Otherwise these two coordinates, they will not necessarily fall on this equilibrium curve. Okay, we'll draw this. So let's try to understand this this flash drum once again. We have the feed here, F moles per unit time, it's brought in, it has a composition ZF, enthalpy HF. Here we heat this liquid to saturated state, we bring it, supply the heat at a rate of calorie per second, liquid is pressurized so that its throttle brought down to the pressure P2. We have this phase separations, vapor and liquid, vapor is withdrawn from here, liquid is withdrawn from the bottom after giving sufficient contact time between the two phases, so that we have the two living streams, vapor and the liquid, they are in equilibrium. So let's assume that we have D moles per second molar flow rates and we have W moles per second of the liquid flow rates. Enthalpy is HT, enthalpy is HW, we have the mole fractions YD and mole fraction of XT. Except when we say that they are in equilibriums, now YD can be written as a function of XW by this equilibrium curve or vapor liquid equilibrium curve, because two streams living are in equilibrium. Let us draw this on TXY as well as HXY diagram. So for this component A plus B, we have this TXY diagram, TXY. So let's say that we have this vapor liquid TXY diagram, and this is, note that, at a pressure P2. So P2 is the downstream pressure of this flash drum, because the liquid has been throttled to the pressure P2, then the two phases have been separated. Now this, if the flash drum temperature is somewhere here T, and the two streams which leave from the flash drum, they are in equilibriums, then we can say that this is a tie line, and this component here, it will be YD, and this component will be XW. So this is the meaning of this equilibrium. For a given pressure P2, fix the pressure, T is the temperature of the flash drum here, in between TB, TA, A is more volatile than B, A plus B binary components. We have fixing YD and XW corresponding to this flash drum temperatures. Okay, so this is your TXY diagram. Now let's plot, and just underneath this, y-x diagram. All right, we have done this earlier also. So 45-degree lines. Now if we take this projection here on the y, 45-degree line, go this way, take x all the way till here, it intersects here. This would be the coordinates of x, this component with xw, and this would be yd, and this point will be on this yxy diagram, y versus x diagram, because we are saying that two streams which are leaving the flash drum, they are in equilibrium. So we have this point here, coordinate is xw and yw, and we must note that this coordinate also corresponds to this temperature T here. Okay, underneath this, now what happens to the, before we draw this hxy diagram, let's look at what happens to ZF, mole fractions of component A in the feed phase. So if we have this flash drum here, the feed was brought in F with the component ZF, and we have YD, total flow rate is D, we have XW, total flow rate, molar flow rate is W. Let's not bring enthalpy right now because we are working on TXY diagram. Now look at this mixing rule, F equals D plus W, this we did earlier, and we can also write F multiplied by ZF equals YD multiplied by D plus XW multiplied by W. Alright, so let's rewrite maybe F equal to D plus W, F ZF equals D YD plus XW into W. Now again we are applying the two mixing rules, which means if we fix the coordinate of D and W, the coordinate of feed F will be on the straight line lying between D and W. Okay, so from this one can show that we'll get minus W by D equals YD minus ZF over XW minus ZF. Okay, it's not difficult to show that. Here if we put YD equal to ZF, this mole fractions of the feed ZF, which is in between YD and XW, this would be on the 45-degree lines, right? Because we put YD equal to ZF, XW will also come to ZF here. So this is your ZF feed compositions. That means if you draw this line here, the slope of this line will be minus W over D, which is same as this. Okay, so let's try to understand here that we are trying to say that two fluids D and W can also be seen as mixed or coming out of this F. If we take F and it's all adiabatic, okay, so we are writing a material balance F equal to D plus W, and there is no loss of the species, FZF equal to DYD plus XWY. That means the coordinate of this F has to be on the straight line joining D and W. So this mole fractions is ZF here. If we put in this equation of a straight line, minus W by D, YD minus ZF over XW minus ZF. If we substitute YD equal to ZF, you will get XW as ZF. Okay, so here if we substitute with this coordinate at 45-degree line here, connect these 2 points, one can obtain minus W by D. In other words, if you take this line and then you take a slope of minus W by D, you will obtain this ZF. Alright, or starting from ZF, if you take this slope of minus W by D, you will obtain YD and you will obtain XW. Similar exercise one can also done on this HXY diagram. So now let's plot HXY diagram. So we have HX, HL, and we have this HV curve here. Okay, we have X and we have Y here. Alright, now we take the projections of this Y. So this stream is saturated, the stream which is living here YD is in equilibrium with this W, this coordinate comes here. If we take XW here all the way for this liquid, we have saturated liquid here. Connect this would be a tie line. That's one thing, because two living streams were in equilibriums. We have YX from this tie line all the way projections, if we do it here, this will also be a tie line. So this coordinate is now xw, this coordinate is yd. Here we have hd, and this is hf plus q over f. So this was the enthalpy of this fluid here. Let's write down hd, we have hw, and here we have this hf plus q over f. Excuse me, so this here is actually, this is hd here, and this one is hw here. Now where is this coordinate zf? Just like we said that zf equals d plus w, we can also write an enthalpy balance f hf. Okay, so we have f hf plus q, this is incoming to the flash drum, this equals d hd plus we have w into hw, and from this and the first equation f equal to d plus w, we should be able to obtain that again we have minus w over d as hd minus hf plus q over f over hw minus hf plus q over f. So one can again apply this mixing rule. There is no heat loss. That means the coordinate of this zf, if we mark it here, this will correspond to this coordinate here, this will has to correspond to hf plus q over f. The very fact that we are adding, we are mixing, right, or we are separating f into d plus w as good as we mix d plus w to obtain f adiabatically. So if we know this coordinate here, we know the coordinate here, you mix the, draw this as a tie line, mark this zf on this, the coordinate enthalpy coordinate has to be the enthalpy of this entering fluid which enters, which is hf plus q by f. Okay, and here also the slope of this line will be minus w by d, that also comes from this geometries. Okay, we will redraw this line hxy diagram again. So we have this y x, we got yd, and we got this xw, and the two streams were in equilibrium, so we have this point here. Underneath, just underneath, we want to take a projections on hxy diagram, hxy diagram. So we have this hv, saturated vapor enthalpy curve, and we have saturated liquid enthalpy curve. Take all the way this projection for y till here to obtain hd, take this xw all the way till here to obtain hw. So we have xw and we have marked yd, we have hw and we have hd here. If we draw these two lines, this would be the tie line, because two streams which were living were in equilibrium. Remember this, this also came from Txy diagram. So if we have this Txy diagram, this was yd and this was xw, and this is the temperature. So the liquid was flashed at this temperature. We had these two living streams yd and xw, which we marked on this, and we take these projections and we mark here. Okay, where is the feed? Here and here. Well, when we make this mixing rule here for the enthalpy and for the species balance, we said that we have a slope from the coordinate geometries minus w by d, amounts of liquid and the vapor living two streams can be shown to be equivalent to yd minus zf over xw minus zf, and this will also can be shown to be equal to hd minus HF plus Q by F over HW minus HF plus Q over F. Okay. So going back to the mixing rule, how do we get ZF? Make use of this coordinate geometry. If you know the mole fractions ZF of the feed, F is a 45-degree line. That means if you connect this, this would be minus W by D. Right? In other words, if I fix ZF and take the slope of minus W by D, I will hit YD and XW. Or if I take YD XW, take the slope of minus W by D, I will reach this ZF. Or if I just take ZF and connect with XDY, YD, XW curve, we will get this line, slope would be minus W by D. So similar argument here. Where is the feed? If I choose feed ZF, in between XW here, then the coordinate of this will be HF plus Q by F, because that's a mixing rule. We are mixing, we are taking a feed which has enthalpy of HF plus Q by F. Is now separated in two streams, D and W. Two are in equilibrium, they fall on the line, on a straight line, and this is given, equation of slope of this line is given by minus W by D. So this is a tie line, and the slope of this line will be minus W by D from here, this relation which we obtain. So it's very important that we understand that TXY diagram, whatever we have done here in terms of marking the coordinates, is as good as HXY diagram, where we have marked the coordinates of two streams which are going to leave, given the feed state composition ZF, and the enthalpy of this fluid as HF plus Q by F. Alright. Now in this case we have assumed that two streams, vapor and the liquid, they leave in equilibrium. So that means when the feed was brought, the superheated, this heated fluid, pressurized liquid, and it was flashed after throttling, we gave enough time, good mixing between the two phases, vapor and liquid, so that the two living streams are in equilibrium. That means one temperature T and YD and XW, they are on the tie line TXY. Okay. So when we take a projections on YX, we mark this point YD and XW. Where is the feed? Well, we choose the feed as ZF, which is entering, and if we connect with this line on the equilibrium curve, the slope of the curve will be the ratios of W and D. That comes from the coordinate geometries, minus W by D. You take further projections on HXY diagram, you should also be able to convince yourself that now the tie line which you join between the HV and HL, right, corresponding to YD and XW, and corresponding to the enthalpy of HD and HW, there the slope of the tie line will also be minus W by D, because two living streams are in equilibrium. There are cases when there is non-ideality or non-equilibrium, and it's possible that the two streams may not live in equilibrium. And then there are several possibilities of non-equilibriums, which we will like to redraw and see on this HXY diagram or on TXY diagram. You can have different scenarios of non-equilibriums, which we take up in the next lecture. Thank you.